During the construction days of the Mount Wilson Observatory, an opportunity came to a man named Milton Humison. Humison drove one of the mule teams up the old observatory trail to carry supplies to the astronomers and construction teams. He became interested in the work of the observatory and took on a job assisting the astronomers. Gradually, he learned more and more about astronomy and eventually became a full-staff astronomer at the Mount Wilson Observatory. Humison's work with astronomer Edwin Hubble was later to play a key role in modern cosmology. Astronomers are still debating some of the implications of this early work, and even today, a note of uncertainty hangs over its implications for the future of the universe. One of the most important discoveries in cosmology is that the universe is expanding. And some of the crucial observations that establish that fact were made right here at the Cassegrain focus of the 100-inch telescope. In the late 1920s and early 1930s, Humison sat on this very platform, operating a specially designed spectrograph to record the very feeble light from remote galaxies. The fact that the universe is expanding means that galaxies are rushing away from each other and from us. But we know about their motion away from us by virtue of the fact that the wavelengths of the light that we receive from them are shifted. But we only detect that shift by spreading the light from a galaxy out into its spectrum, that is the rainbow of colors that make it up. But the image of a galaxy is pretty faint as it is. And when you spread it out, it makes it even fainter. So Humison had to have the light-gathering power of the world's largest telescope, combined with the storage capacity of the photographic emulsion, to record that precious information. The data obtained at the telescopes are analyzed in the laboratories at Pasadena, at the foot of the mountain. The measurement of the spectra requires a precision instrument of a different kind. Here is one of the spectra that Humison took of a remote stellar system. Actually, there are two spectra on this negative. The gray streak running horizontally down the middle is the spectrum of the remote galaxy. The vertical streaks on either side are the spectrum of a comparison source, namely iron, which was put on the same plate during the exposure at the telescope. To measure the motions of the galaxies, Humison used this simple traveling microscope. It's equipped with a precision screw so that Humison could determine the distance along the spectrum of the position of various features that were recorded there. Let's see if we can focus this up now and see what's really going on in the measurement of these motions. Now, if a galaxy is moving away, the frequency is lowered by the Doppler effect. This effect is familiar in the change in pitch of a moving source. The frequency heard from a stationary position is lower than the emitted note when the source is moving away. Of course, sound does not have an absolute speed independent of the observer, like light, but it still serves to illustrate the effect on a mixture of frequencies. In the spectrum of a galaxy, we have just such a mixture, corresponding to narrow dips or absorption lines in the otherwise continuous spectrum. How is that pattern of absorption lines affected by the Doppler shift? Suppose that instead of a solo flute, we had a complete orchestra. The melody is still recognizable and because all of the frequencies are changed by the same factor. That factor is related to the speed of recession of the galaxy by the Doppler effect, as given by special relativity. But our story really begins back in the 17th century, after Newton introduced the idea of universal gravitation. Newton tested his gravitational theory on the solar system, but did not at first apply it to the universe as a whole. He was drawn into the much wider cosmological question by a correspondence with a scholar, the Reverend Richard Bentley. Newton admitted that I had considered it very little before your letters put me on to it. At the time of this discussion, Bentley was chaplain to the Bishop of Worcester and lived at the bishop's palace. His interest in cosmology was sharpened by being chosen to deliver a set of 8 sermons in fulfillment of a bequest of no less than 50 pounds in proof of the Christian religion against notorious infidels. Alan Cooper.
Imagine the situation at that time. There was very little that was really known about the structure of the universe. It was mostly a matter of religious belief about how the universe ought to be. And it had generally been believed that the universe should be static in some way with fixed boundaries. And so when Bentley came to prepare his sermons, he was led to wonder whether such a universe, a static universe, could be produced, let's say, from an even distribution of matter by the action of gravity alone. Because if not, then surely there was the need for the intervention of a god. And it seemed to Bentley that a finite universe under gravity would simply collapse. But he wrote to Newton himself to ask what he thought. And a few days later, he had a reply from Newton saying, "The hypothesis of matter being at first evenly spread through the heavens is, in my opinion, inconsistent with the hypothesis of innate gravity without a supernatural power to reconcile them, and therefore it infers a deity." Well, that, of course, is just what Bentley was hoping to hear. But it wasn't quite as simple as that. What about an infinite universe? Would that be stable? Well, there, Newton's reply was that an infinite universe as a whole could be stable, but there'd be local collapse, lots of local collapses, and perhaps it's that which produced the stars. Well, perhaps this seems rather old-fashioned argumentation as far as cosmology is concerned. But this basic question of whether an infinite universe is needed to produce gravitational stability is one which lingered on for 200 years and more into our present century. On the one hand, it seems necessary, but on the other hand, the idea of infinity is a very difficult one. So there it was, stalemate.
The traditional wish for stability dominated not only religious thought, but also scientific thought right up to the 1920s. Einstein first applied his theory of gravity to cosmology around 1916. But in Einstein's theory, not even an infinite universe can be stable. He was for a while led astray by tradition and tried to impose stability by adding an arbitrary hypothetical term called the cosmological constant. But he was never really happy with this, and his intuition was soon proved right. A Russian cosmologist, Alexander Friedmann, found some new solutions overlooked by Einstein. They were not static and did not need the cosmological constant. Friedman's conclusions were confirmed independently by a Belgian canon, Georges Lemaitre. He was, like Bentley, a priest who became interested in cosmology. He had an inkling that there was a physical basis for accepting this non-static model. Just the title alone of his classic paper of 1927 is, I think, very revealing. He called it a homogeneous universe of constant mass and increasing radius, accounting for the radial velocity of the extragalactic nebulae. You see, he'd spent some time in the United States, and he had a hunch that measurements in progress in Arizona would confirm his ideas. But this observatory, nestling beneath the San Francisco peaks in Flagstaff, had been established for other purposes. Its 24-inch refracting telescope was usually found pointing towards Mars or some other planet in our solar system. You see, the observatory's director, Percival Lowell, passionately believed in life on other planets, and he instructed his staff to pursue this end. It was almost serendipitous that it became involved in cosmology.
One of Lowell's finest young astronomers was Vesto Slipher, who would frequently end a long night of work by passing the light from the iron arc into the spectrograph attached to this telescope to provide the comparison spectrum on his photograph. This is the apparatus that Slipher used to produce that arc. It's rather primitive on our standards, and Slipher, being a very dedicated astronomer, frequently overlooked the rather unique safety features of the device. Slipher was carrying out the instructions of his director, Lowell, who had asked him to obtain spectra of some of the so-called white nebulae. The first object for which Slipher obtained a spectrum was the nearby Andromeda Nebula. He found that the spectral lines were shifted, indicating a motion of that object in our line of sight, with a speed greater than that of any other object ever observed. Well, when Lowell heard of this result from Slipher, he said, "It looks as if you've made a great discovery. Try some other spiral nebulae for confirmation." Well, over the next 20 years, Slipher observed many of the nebulae, and he found that all but a tiny handful are moving away from us and at very great speeds. Years later, Hubble was to write to Slipher that it was his observations at the Lowell Observatory that were the first steps and the most important ones in establishing the expansion of the universe. By 1929, Hubble had estimated distances to the galaxies whose velocities had been observed by Slipher. Just as Lemaitre had predicted 2 years earlier, the more remote galaxies are receding from us at a greater rate. Meanwhile, Humason at Mount Wilson had measured new velocities of galaxies moving away at speeds up to 15 times those of the most remote galaxies observed by Slipher. In 1931, Humason and Hubble jointly published in the Astrophysical Journal the definitive paper that established what is now known as the Hubble law, that the distant galaxies move away from us and at speeds proportional to their distances. The observatories at Mount Wilson were now attracting the attention of leading theoretical physicists, among them H.P. Robertson and Richard Tolman at Caltech in Pasadena. During this period, Einstein and Lemaitre themselves visited Caltech to confer with their California colleagues. Excitement ran high as theories of the universe were debated and developed. Virtually all theories of the universe assume that it is the same everywhere. This assumption is consistent with Hubble's observations that the universe on the large scale appears to be uniform, an idea that the theorists call the cosmological principle.
Hubble's law and a uniform universe go together, linked by general relativity. And a uniform universe is not stable.
But the instability is of a particularly simple type, speed proportional to distance. Simple, but with a very special property, because that's the one type of expansion which is the same at each and every point in the universe.
The cosmological principle is the idea that the universe is the same in all directions and at all distances. How does this relate to Hubble's law that the speeds of recession of galaxies are proportional to their distances? Suppose we idealize a region of space as a grid of lines with galaxies spread more or less uniformly throughout the grid, and we look at a particular part of the grid at only a few galaxies. Imagine we are on galaxy O, and we look at it as it is today and at some time in the future. Because the expansion is uniform, all galaxies keep their relative positions, only the scale of the grid changes. We see that galaxy B is always further from us than galaxy A, and consequently recedes faster than A, because it has further to go in the same time. Faster speed, proportional to greater distance. A uniform expansion results in Hubble's law and applies to all galaxies on the grid. The distance of each galaxy is measured from O to its today position, and speed is measured by the lines drawn to future positions. Now, if we plot the speed vertically against the distance horizontally and compare the other galaxies, we get this, the familiar straight line form. This is for the expansion as viewed from O. But does this mean that O has to be at the center? If we look at the same expansion from galaxy D, the universe in the future would look like this. Indeed, there is no special center to this expansion. Every galaxy is rushing away from all other galaxies. Every observer, no matter where he is, sees the universe expand in the same way. So that's how uniformity and the lack of a center and Hubble's law all fit together. Now, how does this expansion change with time? Because it's the same everywhere, we need only look at the distance between any two arbitrarily chosen galaxies. This distance, for instance, provides a convenient scale factor for the expanding universe. Imagine for the moment that there were no gravitation. Then the expansion would carry straight on. And in this case, the speed, which is the slope of this line that represents the change of the scale of the universe, that slope would not change with time. But of course, in the real universe, there is gravitation, and it slows down the expansion, producing a curve that shows us the evolution of the scale of the universe. The big question is how the scale will change in the future. We cannot, of course, see into the future, but we can and do look into the past. We see galaxies 1,000 million light years away, as they were when light left them 1,000 million years ago. Back then, less slowed by gravity, the galaxies had greater speeds than now, and the slope of the curve showing the scale of the universe was steeper than it is now. The amount of curvature of the line depends on how rapidly gravitation slows the expansion. There are two possibilities. If the overall density of matter is low, gravity is weak, and the expansion will go on forever. But if the density is high enough, gravity will win out, the expansion will one day stop, and the universe will collapse again. So, to predict the future, we look into the past, to times when the scale of the universe was smaller than it is now. The speeds we measure for galaxies very far away are the speeds that they had very long ago. Hence, the precise shape of the Hubble plot depends on how strongly gravitation is slowing down the expansion, and contains a clue to the future of the universe. Unfortunately, with present technology, we are not able to measure distances very accurately for remote galaxies, so the data are not yet good enough to give us a definitive answer. But at least the question is well defined. Will the universe go on expanding forever? Or will gravitation eventually stop the expansion and the universe collapse on itself. High on Palomar Mountain, the great 200-inch reflector has been a principal tool for astronomers searching for an answer. It was founded by the visionary George Ellery Hale, who had previously inspired the construction of the 60-inch and 100-inch telescopes on Mount Wilson, 90 miles north of this site. It penetrates vast depths of space, and today, 50 years on from the basic discoveries made by Slipher and Hubble and Hummerson, fundamental work continues on the expanding universe.
Our story began with Hummerson at the gas-grain focus of the 100-inch telescope. This is the gas-grain focus of the Hale reflector on Palomar Mountain. Above me, 14 tons of glass make up the 200-inch diameter mirror that gathers the fossil radiation from remote galaxies. With equipment somewhat more modern than Hummerson's, astronomers are still discovering ever and ever greater redshifts. Now, the precise form of the Hubble plot does contain the secret of the evolution of the universe. But the observations are difficult to interpret and are still inconclusive. On the other hand, there are many clues that, in principle, should tell us how the expansion of the universe evolves, and, in turn, what our future should be. At present, most of these clues seem to point in one direction, but with considerable uncertainty. Perhaps the best indication of the future of the universe is its present-day density. Is there enough gravitation to stop the expansion, given its present rate? The best answer we can give today is no. It appears as though the universe may go on expanding forever. It's as if gravitation, that force so familiar that binds our solar system together, is not important enough on the universal scale. Now, if this is so, and we're by no means sure of this, it means that we are living in a one-time universe that will expand forever into nothingness, darkness. As Alan Sandage, the astronomer at Hale Observatories, who has followed in the footsteps of Hubble, has put it, the universe may have happened only once.